So we have problem number 12 on the Advanced Classical Mechanics Practice Final Exam. So let's begin. Consider the periodically driven damped pendulum, theta double dot plus gamma theta dot plus omega naught squared sine theta equals a cosine of capital omega t. Part A, convert the system into a first order autonomous system. Part B, identify fixed points in the undriven, undamped limit. Part C, explain the difference between periodic, quasi-periodic, and chaotic trajectories. Part D, define a Poincare section for this system. Part E, explain how sensitive dependence on initial conditions can be diagnosed. And Part F, discuss the roles of damping and driving in the appearance of attractors. So this is a nonlinear dynamics and onset of chaos problem. So beginning with part A here, so convert to first order autonomous system. We're going to let x sub 1 equal theta, x sub 2 equal theta dot, and x sub 3 equal capital omega t. So then from here, x sub 1 dot equals x sub 2, x sub 2 dot equals negative gamma x sub 2 minus omega naught squared sine x sub 1 plus a cosine x sub 3. X sub 3 dot, that's going to equal capital omega. So the autonomous system is going to be here x sub 1 dot equals x sub 2. X sub 2 dot equals negative gamma x sub 2 minus omega naught squared sine x sub 1 plus a cosine x sub 3. And also here, x sub 3 dot is going to equal, again, capital omega. And since x sub 3 is a phase variable, we could state the following relationship between x sub 3 and x sub 3 plus 2 pi. So the dynamics transpire on the extended phase space, and we have theta, comma, theta dot, comma, capital omega t mod 2 pi. Okay, so building on that for part B. So part B, fixed points in the undriven, undamped limit. So we set a equal to 0, gamma equal to 0. Then theta double dot plus omega naught squared sine theta, that equals 0. And as a first order system, theta dot equals v, and v dot equals negative omega naught squared sine theta. And our fixed points satisfy v equals 0 and sine of theta equals 0. So therefore, theta equals n pi, and n belongs to the integers. So the fixed points are 0 comma v, theta comma v equals n pi comma 0. Again, where n belongs to the integers. And for even n, theta equals 2 pi k, and the pendulum is hanging downward. So these are stable centers. For odd n, theta is equal to the quantity 2k plus 1 times pi, and the pendulum is upright. And these are unstable saddle points. So we could conclude from there that points for 2 pi k comma 0, those are the centers, and for the quantity 2k plus 1 times pi comma 0, those are the saddles. Okay, so moving on to part C, periodic, quasi-periodic, and chaotic trajectories. So a periodic trajectory here after some time t, that can be here classified as this theta lowercase t plus capital T equals theta of lowercase t, comma, theta dot of that lowercase t plus capital T equals theta dot of t. Okay, so here are our two relationships here. So for the driven system, periodic motion is often locked to the driving period. T sub d equals 2 pi over capital omega. And a quasi-periodic trajectory involves two or more incommensurate frequencies, and it never exactly repeats. But it remains confined to a smooth torus-like set in phase space. And a chaotic trajectory is deterministic but highly sensitive to the initial conditions. So nearby initial states separate exponentially for some interval of time. So here we have the magnitude of delta x of t scales to the magnitude of delta x of 0 e to the lambda t, where lambda is greater than 0. So here lambda is a positive Lyapunov exponent. Okay, so that's part C, and then moving on to now part D. For part D, we want to define a Poincare section, and because the system is periodically driven, the natural Poincare section samples the motion once per driving period. T sub d equals 2 pi over capital omega. And we define the stroboscopic map. Here we have theta sub n comma theta sub n dot equals theta of n t sub d comma theta dot of n t sub d. So equivalently sample whenever capital omega t equals 2 pi n. And since theta is angular, we can plot theta mod 2 pi against theta dot. So for periodic motion, the Poincare section contains finitely many points. And for quasi-periodic motion, the section gives smooth closed curves. And for chaotic motion, the section produces a scattered fractal-like set. Okay, moving along to part E. Sensitive dependence on initial conditions. So sensitive dependence can be diagnosed by evolving two nearby initial conditions, x of 0 and then x of 0 plus delta x of 0. And if the separation grows approximately as the following, the magnitude of delta x of t is approximately the magnitude of delta x of 0 times e to the lambda t, with lambda again being greater than 0. Then the system has a positive Lyapunov exponent and is chaotic. And in practice, by computing, we have the following: lambda equals the limit as t approaches infinity for 1 over t ln magnitude lambda x of t over magnitude lambda x, ln magnitude delta x of t divided by magnitude delta x of 0. Sorry about that, not enough coffee. So those are deltas, and my apologies for the poorly constructed deltas. And we can add to this a positive largest Lyapunov exponent is one of the strongest diagnostics of chaos. All right, now building on this for part F, that was part E, now letter F. The roles of damping and driving. So the damping term is gamma theta dot, and it removes energy from the system. The driving term is capital A cosine of capital omega. The driving term is capital A cosine of capital omega t. And it injects energy into the system. Without damping and driving, the pendulum is conservative. Its phase space trajectories lie on constant energy curves, and the system is integrable. With damping alone, trajectories lose energy and approach stable equilibrium. Okay, building on that for the rest of F, now we move to driving. With driving alone, energy can be pumped into the system, but the system remains non-autonomous and can exhibit complicated behavior. With both damping and driving, the system can reach long time attracting sets. And these may be fixed points, periodic cycles, quasi-periodic attractors, or chaotic attractors. And we can say that the balance between energy input and energy loss is what allows strange attractors to appear. Okay, so that is problem number 12. Thank you very much and have a great day.